can see that, but now we're recording. So, again, let me start over again. We're in Chapter 2, Matrices, Section 2.1, Operations with Matrices, and we're on page 46. Now, I didn't ask this before, and maybe I should. I don't know why I've got the screen at the bottom now. Okay. Do all of you have books? James, Alea, and Jermanuel, do y'all have?
Not yet.
Not yet, you said, Alea?
No.
Okay.
No.
All right. Are you on Cengage Unlimited?
Yes.
You are. Okay. Well, you should be able to get one through them, and you should be able to get it fairly quickly. The thing is, I don't know how they do it, but you'll see the course code is out there. You know where it was in the other class, same place in this class. Go to
Yes.
Blackboard content and look for the campus key, or whatever they call it, course key, whatever they call it, and there it is, and you should be able to access your book that way. That will be an ebook. If you want a paper copy, are they doing PDF forms now? In another class, it sounded like they were. Rather than you having to buy one for $8, you can get a PDF version. Well, I'll let y'all figure that out, but it's fairly easy to do. Jermaine, do you have a book? Jermanuel, do you have a book?
I think I did.
Okay. All right. Yeah, I think Ricky sent you one, didn't she?
Yeah, I did.
Okay, right. Okay, yeah. You got one of those. And actually, a student in my last class said, "Do you want me to send you a PDF?" I thought, is that legal? I mean, I don't want to break any laws here. And she said, no, Auburn was doing it all with the, whatever you call it, the COVID-19 and stuff. They've relaxed things a lot. So evidently people are able to share PDFs, which is, I'm surprised the book publishers put up with that, but they do. All right.
Did we do all the chapters of chapter 1 or?
We did all the sections in chapter 1, but the third section, there's not much on the test on it, if my memory's right. I don't recall if there's maybe just one or maybe none on it, but if you listen to YouTube videos, you'll get which ones we skipped and which ones we did. Like we didn't do polynomial expansion. That was just a little too involved and awkward and things like that. So it comes in useful when you're doing linear regression, but since we're not doing linear regression, I kind of skipped it. We did do the Kirchhoff's laws and other, whatever you call that, network problems, just because I figured y'all would be doing that in physics. I knew all engineers took physics, so I wanted to go on and get that one done for you. May wind up doing whatever I just said, linear regressions at some point in your career, but you're probably going to have to learn it from there. So it's just an application of matrices. All right. Any other questions? All right. On page 46, if you got a book or if you don't, we're talking about partition matrices again. And they go into this, and they do a fair amount of stuff with it, but they very seldom use it. So let's do it, but I sure don't want to write everything down. So when I can get away with it, I'm just going to hold up my picture. I know Alea doesn't have the book yet. And is it Alea or Alea? I can't remember.
It's Alea.
Alea. Okay, Alea. Sorry, I've been saying it wrong. Yeah. She doesn't have a book, so I'm going to hold up mine so that you can see what we're talking about. Now, and I think in my other class too, I've started writing on the whiteboard a lot, right?
Yes.
Okay. So here it comes again, the good old whiteboard. And you probably can't see this, but I have a taskbar at the top that they always sort of put in the way. So I'm going to bring it up here. And then they have a taskbar at the bottom that is just about always in the way. So I'm going to move it down here. You can't see me doing either one of them. That's why I'm wasting time right now trying to get them out of the way so I can have more of the board to write on. So, Aaliyah, here's what we're talking about a whole lot especially in this chapter. We got close to it in the first chapter, but if you have a system of equations, now you probably from earlier courses, you would do something like x plus 2y is equal to 4 and 7x minus 2y is equal to 3, okay? That would be a system of equations, pretty small, pretty short, pretty sweet, and you could just do it elimination by addition, okay? You could go up to 3 by 3s and do them. They got a lot messier. But anything 3 by 3 and beyond is so much easier to do a system of equations by matrices. So here is the shortcut for writing a system of equations using a matrix. Matrices are usually given capital letters, and that stands for the coefficient matrix of your system of equations. Okay? Your variable, now, if you just have two variables, x and y will do. And when you have 3, x, y, and z will do. When you have 4 or more, you have to start using more letters. There may be w, x, y, z, okay, and maybe 5 or more, whatever comes before w, u, v, w, x, y, z. I mean, the letters get in the way. So in this text and in a lot of texts, after a while, we start using just subscripts. So we'll say x of 1, x of 2, x of 3, rather than x, y, z. So in other words, x is your variable, but it can represent several different variables, and the subscripts represent which variable you're dealing with. So therefore, since it's a subscripted letter, we call that a vector. Okay? Okay, so AX, where X and B, X1, X2, X3, X4, as many as you have, is equal to, and A is your coefficient matrix, so you have constants at the end, okay? Well, that would be represented by a vector they call B, because you have several of them as well. So that's how we, rather than writing an entire system of equations, we just shorthand it to coefficient matrix times your x vector is equal to your b vector. Okay? Now, and normally I wouldn't do this now because it's your first time. I'll do it now. Here is your typical coefficient matrix. In generic terms here, and we all know and love it so well, we could sing it by heart. Okay? The first coefficient, okay, I'm going to write and then I'll come back and explain. A11, see, capital A is the name of the matrix. The individual elements of that matrix, these are the individual coefficients of those variables. They're given they're written in lowercase, usually the same as what the capital is here, and they're given 2 subscripts, and we'll go into that in a minute. In fact, you may be able to figure it out just watching. A11, A12, A13, and my pen has started skipping some, I don't know why, and we'll just do a dot, 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 and go all the way up to A1N, okay? And then the second row of the matrix will be A21, this will be A22, this will be A23, and we'll have another set of dot, 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 and get up to A sub 2N. Okay? And then we'll have another one that will be A sub 3,1, A sub 3,2, A sub 3, 3. And another dot, dot, dot to get us up to A sub 3n. This is almost as much fun as watching paint dry, isn't it? Okay. And we'll just dot, dot, dot down the row here, down the column here, and finally get down to A sub, that's supposed to be an A, sub m. 1, A sub m2, getting a little out of control here, A sub m3, it's supposed to be a 3, a dot, 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 and our finally here is an A sub m n. Okay, and there's dot, dot, dots all here, and here, and here, and everywhere in between. Okay, always a dot, dot. Okay, okay. Fills in all the thing. This is your matrix. In matrices, we usually enclose those elements in square brackets. Okay, so there's your matrix A. Your matrix X, you can call it a matrix. It's called a column matrix or a column vector because it only has one dimension in one way. And since it's a column, that's in your column. These are your X sub 1. Here comes Ricky. Good deal. Perfect attendance today, folks. Way to go. Okay. Ricky's here. Aaliyah, you brought out the best in them. Okay. Aaliyah, sorry. All right. Hopefully, Ricky. Oh, Ricky, are you already able to hear? No, you're still connecting to audio. Okay. You might be able to see. Okay, Ricky, you here?
Yes.
All right, good deal. We have Aaliyah in the class now. She just added recently, but today's the first day of class. So now you've balanced out the X and Y chromosomes. Okay, so that works well. Okay. So here's your column vector. We're talking about this matrix equation here. Matrix A times column vector X is equal to column vector B, where A is this matrix coefficient matrix, and then I'm doing the X part. That was the A part. Here's the X part. X sub 1, X sub 2, X sub 3. These are your different variables. That if this were only 3, that'd be X, Y, and Z. But we're calling them subscripted now. And we'll dot, dot this down to, and in this case, we only have, and this is supposed to be an X. It's not looking like an X. X sub n, because we have n variables. And we'll talk about this in just a minute too. I'm going to see if I can erase some of that ugliness there, because that didn't become what I wanted it to become. There, I did. Amazing. Okay. Now that's equal to, now here's the B part. This is this column vector B. Column vector B, that's ugly, is B sub 1, B sub 2, B sub 3. Now these just represent any old numbers. There's nothing special about the B. It's just what we usually call it. And it'll dot, dot, dot down to, and the last one of these happens to be B sub M. Okay, I'll go over the reason for this in a minute. Okay, I didn't quite, it's ugly. I'm sorry, it's just ugly. Now, that represents your system of equations. And what is that system of equation? And Aaliyah, this is how you do matrix multiplication. Okay, well, let me start off with what these subscripts mean. The first subscript identifies which equation number you are, which in matrices we often call row number. So notice everything in the first row is the first subscript of 1. Everything in the second row has a subscript of 2. That means that's which row or which equation you're dealing with. Everything in the third has a subscript of 3. And on the mth equation, so we have m equations. So the last one here will be a sub m1, a sub m2, a sub m3. These are the coefficients for in that last row or last set of equation, last equation in the set. So you have m rows, you have n columns. Well, the n columns, because these are the coefficients of your various variables, that means we have n variables that we're calling our x's, x of 1, x of 2, up to x of n. That's why its subscript is an n, because, and this is how you do matrix multiplication. I wish I had two markers to move at once. You go down this way while you're, across that way while you're doing down this way. So it'd be a11 times x of 1 plus a12 times x of 2 plus a13 times x of 3 plus a blah, 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 a1n times x of n. So the second subscript identifies which variable you're dealing with. The third variable would be your sub 3's, and all this column in your A matrix will represent the coefficients for that third variable. And it says in the first equation, the second equation, the third equation, always of that third variable. It's a13 x of 3. This would be a23 x of 3 plus a3. But you don't add them this way. You add them going across here. But they would be the same. Now, your b's represent your constants at the end. And since you have m equations, that means you only have m b's. You have n x's because you have n unknowns here, n columns, but you have m constants because one constant for every equation, and you have m equations. So that's b1 through bm. So this is the shorthand that represents, and this really is a little bit of a shorthand, because if you wrote out all the equations, you'd have to write out x1, x2, x3, x4, x, all the way up. Every one of these had to have an x after it, because they're correct x after it. So you just have a lot more writing. This condenses it as much as you can. All right. Now, that's what the initial top several lines in the book does. Okay. Now, what they're going to do here, not my nose is itching, I'm sorry, we must be going to have company, and we can't have company because it's COVID. No, whatever. All right. Another way you could do this is this. If you think about what I just was saying, this is a11 x1 plus a12 x2 plus a13 x3 plus a14 x4 plus a1n x of n is equal to b1. And then you have the same thing here for the b2. But you see, these are all going to be multiplied by your... Sorry, let me drink some water. I don't know. I ate a couple of almonds in between classes, and it must be I've got something stuck in my throat, so sorry. Because on Mondays and Wednesdays, my classes start at 11:30, and I go until 6:15. So I have to eat my lunch from 10:30 to 11:30 on those days. On Tuesdays and Thursdays, I start class at 8:30 and go till 1:15. So I don't get to eat lunch until 1:15 on those days. So what that means is I'm not really hungry on Monday, Wednesday, but I eat, and then the good old stomach says, oh, I like being fed at 10:30. And then on Tuesday and Thursday, when I'm in the middle of class at 10:30 and 11:30 and 12:30, I say, hey, feed me, feed me. So that's why I tried to get a little bit of something to keep my stomach from growling during class. And now I got something stuck in my throat. Sorry about that. So what you can see here, this column all multiplies by the x1s. This column all multiplies by the x2s. This column all multiplies by the x3s, and so on until the final column multiplies by the x of n. And when you do all those together, they still give you the b1s, b2. So that's why the next line in the book, and they actually write them out, and I really don't want to write them out, but I guess it might be helpful. Yuck. I hadn't thought of this, but I guess I should do it. Okay, so let's write out what those individual equations are. Okay. A11, X1. My waving my arms may work a little bit, but it's not really good. Plus A12, X sub 2. So we're going back to writing our system of equations. We're going to put them in matrix form. A13. And this is basically doing our matrix multiplication like I just said. You multiply this row by that column. Okay? So obviously the number of columns in this matrix here has to equal the number of rows in this column here. Okay? And that has to be true. And then we do our plus dot dot dot. And the last plus then is a sub 1n times, oh, I left off my x here. This is x sub 3, and this is a1n times x sub n. Okay, we're going to do that for every one of them. Yuck, that's not supposed to have a jig in it there. I don't know where it came from. And rather than write all the b's here, they're just going to be there, so I'm just going to leave it like the book did as the vector b. Now in the book, a bold letter represents a vector, which could be a column matrix or a row matrix, or row vector, column vector. You can call it either one. Okay? And the second would be a21, that's supposed to be a 2, x sub 1.
So after we multiply x1 by a11 and so on,
Right.
we'll add them.
You what?
After we multiply x1 by a11 and so on, we'll add them.
Yeah, you're multiplying and adding. Yeah, you're absolutely
Okay.
right. That's what you're doing. Multiply, add, okay? And I do want to curtail this as soon as I can, because this is so hard to write. A23, x sub 3, plus dot 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 plus a sub 2n x sub n. Okay, now just picture the rest of those filled out there as it is, and what you'll notice here is all this column right here would be that column, the first column of your A's here. That's exactly what it is, but they're all multiplied by that x1. So another shortcut you could do then is make this column vector of your first coefficients a11, a21, a31, dot dot dot, a sub m1, because you have m rows. Okay, that would be a column vector, and every one of these is multiplied by your x sub 1. Okay, and then add to that your next column, which is your a sub 1, 2, a sub 2, 2, a sub 3, 2. Is this getting as agonizing for you to watch as it is for me to do? Dot, 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 down to a sub m2. Okay, and those are all multiplied by your x sub 2 variable. Okay? That stands for some variable x2, whatever that variable is. And you go on all the way across there, and now you've wound up with a series of column vectors multiplied by a variable. And these are all numbers here. This is a variable here, numbers here, variable there, numbers here, variable there. And finally, you get to the last one, and that will be equal to a column that would be your B's, B1 through Bm. These all have M elements in them, in every one of those. So what you've effectively done is taken this matrix equation here and rewritten it, and I don't know why they now reverse the order of them, but they do, and it doesn't really matter because it's all commutative. But I'll do it the way the book does. X sub 1, that's this variable here, down here, times this column vector, I'm calling your A, they call it A1 vector. Now this, remember, is a variable now. This now becomes a vector because that represents this entire column here. I would have called it A sub I1. They just called it A sub 1. Okay? And then the next one would be plus, oops, that's a big plus, isn't it? X sub 2, that's the one from here, the variable here. That looks like a Y, but that's an X sub 2. And then that would be times that next column vector of numbers, they're calling A sub 2. Okay? Now again, they're doing all this, and I'll let you look at how they phrase it in the book, and that's exactly what you have here. So what you have now is a linear combination of column vectors times some variable. Okay? And you have all n of those because you have n variables, n products like that, and that's equal to some constant there. So we call that a linear combination of column vectors. And then they don't do, well, yeah, I guess they do something else with it. So let's get away from the variables and just get to dealing with numbers. Is it okay? That was sort of the theory of it, though it's not really much theory to it, it's just how you do it. Let's actually do this. Can I clear this already, or anyone still writing? If you can't write as fast as I can, we need to get you in some... No, I'm just kidding. All right to erase? Okay, since I don't hear any objection, I'm going to erase. Okay, let's do example 7. Here's how a linear system of equations looks. Okay? X sub 1, this is old hat to the rest of you, but Aaliyah may not have seen it recently, plus 2x sub 2. Now, rather than a's, you're actually giving numbers to it. X sub 2 plus or minus plus 3x sub 3. This is a real creative set here. 3x sub 3. Most of the time they're not this orderly, and that's equal to 0. That's your B1 is your 0. Okay, and again, these coefficients are pretty unrealistic, but I guess he just was tired of making up new ones. So 4x sub 1 plus 5x sub 2, really creative here, isn't he? Plus 6x sub 3 and I think he sets that equal to 3, doesn't he? Yeah. And then he has 7x sub 1. Again, very creative on his coefficients here. Plus 8x sub 2. I guess you realize I'm having to write this on my pad, the keypad down here. So the tip of my finger, sometimes it sticks, sometimes it takes off and does what it wants to. The pad does, I don't know. I think this is all equal to 6. All right, there's your system of equations. All right. Now, based on what we did before, the end of what we were doing on the previous slide, we took all our x sub 1s. I think they write them in front. I don't know why. I would have written them behind, but they write it in front. It doesn't matter where you write it. Your first variable here is multiplied by the first column coefficients here. And if you don't see a coefficient there, but you do see a variable, you understand that coefficient is 1. Okay. If you're missing a variable, then the coefficient is 0. So that's to be a 1, 4, 7. You see, this is easier to write because I'm not having to write so many x sub 1s. Just write it once and I'm done. Here's the 1 x sub 2 I have to write, not 3 times, but once. And then the column of 2, 5, and 8. Okay, column vector there. Plus the variable x sub 3. And its column is 3, 6, and 9. Should be more in line with each other, but fingers getting tired, is equal to, and then you have the column vector here. Oh, way too long. 0, 3, 6. Most of the time I slash my zeros, but when I'm writing with my finger, I avoid any extra marks that I can. Okay. So that's supposed to be how that looks. All right. Now, this may be new to you, Aaliyah, but using Gauss elimination, you can show that this system has infinitely many solutions, one of which, and they just give you here. Now, since Aaliyah wasn't here before, let's do a quick review of Gauss elimination. Okay? Now, this isn't what they're doing here. We're going to leave that over to the right. Let's go back and do it the way we were doing it in Chapter 1. Okay? In Gauss elimination, we write the coefficient matrix and augment it with the constant matrix. So that would be then just the coefficients. 1, 2, 3, 0. 4, 5, 6, 3. 7, 8, 9, 6. All right. There is your matrix we're going to try to deal with. I didn't leave enough room on the left-hand side, so you're going to have to just imagine. I'm going to say it, but don't have room to write it. Now, someone tell me what's your first thing you want when you're trying to do Gauss elimination?
1 in the upper corner.
Yes, you want a 1 in the upper left corner, and thank goodness you got one already. You didn't have to do a thing to do it. Okay, now, Aaliyah, okay, someone tell me, what are the 3 operations you can do that are produce row equivalent or produce equivalent matrices. 3 operations you can do.
Add one row to another.
Add a multiple of one row to another row. That's certainly doable, and we're going to do that next. What's another operation we can do?
Multiply by a non-zero.
Multiply or divide by a non-zero number. A single row by that. That's a legal thing. And what's the other one?
So can you switch rows?
Switch any 2 rows you want to. Okay? Those are the 3 allowable operations, and that's all you really need. So we're going to use the first one that he mentioned, that James mentioned here. We're going to multiply. This is called our leading 1 now. That's why we wanted that first entry to be a 1, to be a leading 1. We're going to multiply the first row by a -4. So when we add it to the second row, this becomes a 0. Because what do we want to happen? Now they said Gauss elimination. We're going to do Gauss elimination. We want, under every leading 1, we want to have all zeros. So that's why we want this 4 to become a 0. So we multiply the top row by -4, add it to this one. That will make this become a 0. So I'm going to write that here. I didn't leave enough room. I should have done it to the side. -4 times row 1. You could think of that as equation 1. Row 1, and add it to row 2. Okay, I usually do that off to the side. So this is going to produce our first row equivalent matrix. Okay, now since we're using the leading 1 in row 1, we don't mess with row 1. Leave it alone. 1, 2, 3, 0. Now that's sort of the boring thing about linear algebra. You just write the same things over and over and over again. But it's still simpler than doing it any other way. So now we do to row 2 what we said we were going to do. -4 times row 1, add that to row 2. So -4 times 1 is -4 plus 4. Of course, that gives us the 0 we were looking for. -4 times 2 is -8 plus 5. That would be a -3. And again, the thing about linear algebra or matrix operations, you're doing really simple operations. You're multiplying and adding. But you're just doing a whole lot of them, and doing a whole lot of them, it's easy to make a mistake. And once you make a mistake in one of them, everything goes to pot. Okay? So continue our process here. -3 times row 1, that'd be -4 times 3 is -12 plus 6 would be a -6. Okay? And finally, the last entry, -4 times 0 is 0 plus 3 is 3. Follow that? All right. So we have a 1 in the upper left. We have a 0 below it. We want a 0 down here. Now, this is where it gets a little sticky. To get this to be a 0, do similar to what we did before. And really, this should have been written next to row 2, but I didn't have room. What I'm going to write now should have been written next to row 3, which is going to be below that. So we're going to do, again, use your leading 1, -7 times row 1, add it to the row 3, and you're going to get a 0 there. So that's what we're going to do. -7 times row 1, and add it to row 3. That's the rule we're going to use, and that's a legal thing, adding a multiple of one row to another row. So -7 times 1 is -7 plus 7. Ha! That's the 0 we were looking for. Okay? -7 times 2 is -14 plus 8. That's a -6, right? Then -7 times 3 is -21 plus 9. I think it's going to be a -18, isn't it? Minus 21 plus 9.
Well,
No, minus 12. I can't add. I'm glad somebody can. Let me get my eraser down here. Okay, he's laughing at me. Okay. I'll remember that. You just lost 17 points, okay? All right, so let's go again. Minus 7 times 3 is minus 21, plus 9 is minus 12. Okay. Not only can I not write, I can't add either. That's supposed to be a 2, okay? And I'll do this one. Minus 7 times 0 is 0, plus 6 is 6. Can you top that, James, huh? Okay.
no, sir.
All right, good deal. So here we have what we want in the, we have a leading 1 in the first row, zeros below it. The next thing we want, now I'm going to carry this in gory detail. James is ready to quit right now. But in gory detail, the next thing I want is the first non-zero entry in the second row. And we'd love it to be in the second column if possible. We want that to be a 1 because we want the first non-zero entry in each row to be a 1. Well, how do we change a minus 3 to a 1? Divide by negative 3. Remember, that's the second rule that we can do. Multiply or divide any row by any non-zero number. Don't ever multiply or divide by 0. You can't divide by 0, multiply by 0, wipe out all the meaning. So divide by negative 3, perfectly legal. So this will be row 2 divided by negative 3, and that will be the new row 2. So this is usually more detail than we give, but just to show Aaliyah how this works. Whoa, that's an ugly error, isn't it? Okay. Now, all we're changing is row 2 now. So row 1 stays the same. 1, like I said, you're just repeating a lot of things over and over and over. 1, 2, 3, 0. Okay. Then divide row 2 by negative 3. 0 divided by negative 3 is 0. Negative 3 divided by negative 3 is 1. Negative 6 divided by negative 3 is 2. And 3 divided by negative 3 is negative 1. Okay. Now, normally we wouldn't have even done that, but we're going to do it now. Okay. Now, what do we want next? Okay. Next thing, after we get a 1 here in this row, we want the entry below it. Well, let me go and write them down. I'm trying to skip a step because I hate writing this stuff. So here again, you just copy this last row down. That's a 0, not a 6. Okay, that's a 0. Okay, this is a minus 6. This is a minus 12, I think, if James got it right. And this is a positive 6. Okay. Okay. Now, what does that lead to? Whoa! Now we've got a 1 here, zeros below it. Leading 1 here, we want zeros below it. Now, Aaliyah, if we were doing Gauss-Jordan elimination, we want zeros above and below. We're just doing Gaussian elimination, so this is just zeros below it. And this is called row echelon form. If you did Gauss-Jordan, you got zeros above it, you call it reduced row echelon form. If you go back and read the first chapter and do the problems, you'll see how all these names start making sense after a while. I know right now it doesn't. Okay, so you're going to use this leading 1 here to try to get this negative 6 to become a 0. And how would you do that?
Row 2 by row 3.
By a positive 6.
Yes, sir.
Okay, yeah. So it's 6 times row 2. That's a 2 there. And add it to row 3. All right. So we're not using row 1 alone, so we write it down again. This is what makes it so boring. 1, 2, 3, 0. Okay. And second row, we're using that leading 1, so you write it down. 0, 1, I believe that's a 2, and that's a negative 1. All right. The third row, we're going to operate using this rule here, 6 times row 2 plus row 3. So 6 times 0 is 0, plus 0 is 0. See, once you got a 0 in place, you don't want them to mess up. Okay? Next, 6 times 1 is 6, plus a minus 6. That's going to add to 0. That's exactly what we wanted it to do. Now, 6 times 2 is 12. And 12 plus negative 12, that goes to 0. Okay? And then finally, 6 times a negative 1 is negative 6 plus 6. Uh-oh. That goes to 0. What does this tell us? Infinite number of solutions. And why? Think back of what this is telling us. This is saying 0 times x1 plus 0 times x2 plus 0 times x3 is equal to 0. Guess what? That's always true. Always and ever, now and forever, always true that 0 times anything plus 0 times anything plus 0 times anything is always going to be 0. And since that's always true, that means you have an infinite number of solutions. Well, that's not totally true. You can have a row of zeros at the bottom that's just an extra row. But what makes it infinite number of solutions is that you don't have enough leading 1s up here. This third variable here, you do not have a leading 1 for it. Okay, so this becomes your arbitrary parameter. Okay, we'll get to that in just a minute. So, if, however, this would have come up as 0, 0, 0, 17, what would that have told you? No solutions. Because 0 times x1 plus 0 times x2 plus 0 times x3 cannot be anything but 0. So if you ever came up with a row, and this was representing a system of equations like this, and you have zeros for all of your coefficients, and this, by the way, is called this is your coefficient matrix, and it's augmented with the constant vector. Okay? So that's what made you 3 rows by 4 columns. Okay? If you came up with a row that said 0, x1 plus 0, x2 plus 0, x3 is equal to anything other than 0, no solution. Nothing will ever make that work. Ever. Ever, ever, ever. But with a 0 out there, you could have infinite number of solutions. And this is what gives them to you. Like I said, this represents the coefficient of x1, coefficient of x2, coefficient of x3, the constant. That's exactly what we have here. This represents coefficient of x1, coefficient of x2, coefficient of x3, this. And this doesn't give us anything. So basically, since we don't have a leading 1 here, we let x3, and I'm going to write it down this way, let x3 equal to some arbitrary constant, and the book's favorite is t. It could be R, S, T, U, V. It could be anything. They love t best. Okay? Now, from this, let's use the second equation. Since the third equation tells us nothing, 0 is equal to 0, that's all it tells us. Let's use the second. What does the second equation say? Second equation says there's nothing times x1 plus x2. Remember, if you have a coefficient of 1, you can just leave it alone. x2 plus 2x3. But guess what? x3 is t. So it's plus 2t is equal to minus 1. That's what the second equation tells us. Well, let's just rework that. Subtract 2t from both sides, and you have x of 2 is equal to, And I don't care which way you do, they're both negative. So negative 2t minus 1. Or minus 1 minus 2t, it doesn't matter. Okay, what does the first equation tell you? First equation says that x1, because its coefficient is 1, it was at the beginning, plus 2 times x2, right? But here's what x2 is. So I'm going to put x2 in parentheses here, negative 2t minus 1 plus 3, that's the coefficient up here, times x3, but x3 is t, so that's plus 3t is equal to 0, because that's what it is here. Well, let's combine everything there and see what we get. This is x1, and plus 2 times minus 2t would be a minus 4t. This is getting pretty ugly. And plus 2 times minus 1 would be a minus 2. And then plus 3t is equal to 0. I don't know if you can hear it or not, but my stomach's growling like crazy. Sorry if you can. All right, let's combine like terms then. And this gives us x sub 1, that first variable. And here you have a minus 4t plus 3t. It's just going to be a minus t minus 2 is equal to 0. Right? Everybody agree? Now let's just add these to the other side, and you get the x1 is equal to t plus 2. T for 2 and 2. No, that's something else. Okay? So what does that tell you? For some arbitrary constant t, x1 is t plus 2, x2 is minus 2t minus 1, and x3 is just t. And that's what your book says. Gaussian elimination shows you this system has infinitely many solutions, one of which is, and they just happen to choose the x3 equal minus 1. So if x3 is minus 1, x1 would be minus 1 plus 2, so that would be 1. x2 would be, if t is minus 1, it would be minus 2 times minus 1 is plus 2 minus 1, so x2 would also be 1. And x3 is what we chose to be, for some reason, I don't know why, chose to be negative 1. So 1, 1, minus 1 is a solution for that system of equations. Okay? Now, Gaussian elimination told us that, so we know it's true. And the book says it too. X1 equal 1, x2 equal 1, x3 equal minus 1. And what they're saying is, well, if you plug those numbers, which we know to be true in here, 1, 1, and minus 1, let's do it and see what we get. 1 here, that would just be 1, 4, 7. Plus, and a 1 for x2. That's what we had here. So that would be a 2, 5, 8, That's an ugly 8, isn't it? Okay. Plus, or actually minus, x3. Minus x3 is -1. So I'm going to make it a plus, but then I'm going to negate everything in that third column. So that'll be a -3, -6, and a -9. And let's see what those three things add to. And by the way, Aaliyah, you probably weren't here to hear how you add matrices or vectors. You add corresponding components. So 1 plus 2 is 3 minus 3 adds to 0. Well, that part works. Let's do the next one. 4 plus 5 adds to 9 minus 6 is 3. Hey, look at that. That part worked. And then 7 plus 8 is 15, minus 9 is equal to 6. And sure enough, that part works too. So yeah, that works. Now, why they chose t equal -1, I mean, it's perfectly fine. I'm really lazy. I would have chosen t equals 0. Okay? When t equals 0, this would be 2. That would be a -1, and that would be 0. So if you do a 2 here, that would be 2, 8, 14. And then this would have been a -1. -2, well, 2 minus 2 is 0. And by the way, the last one is 0, so this one will be completely out of the picture there. So you have a 2 minus 2 would be 0. You'd have a 8 minus 5 would be 3. And you would have a 2 times 7 would be 14 minus 8 would be 6. That works. Anything that will work here in this solution here, when you plug in t, any number in the world, same number for all of them, any number in the world that will make this work. So you have an infinite many solutions. Infinite many ordered triplets, x1, x2, x3, that makes this system of equations true. Infinite number of them. Okay? And that's, I guess, what they're trying to show here. All right. Now, it says, just as you partition A into into columns, and X into rows, it's often useful to consider an M by M matrix partitioned into smaller matrices. And they do all this, and they really don't do much with it. So rather than write all this down, I'm going to show it to you in the book, because this is, and when I get behind the book, it's hard for you to hear me. I understand that. I think that's what I'm trying to show. No, that's the problem. Here's what I'm trying to show. Okay? You can have this matrix, the one we just, no, it's a different matrix. 1, 2, 0, 0, 3, 4, 0, 0, yeah. Do that matrix there, okay? And partition it 2 by 2, 2 by 2, over 1 by 1, or 1 by 2, 1 by 2, okay? Partition it that way. Or you can partition it all into columns. And that would be how the columns did. So you can change that to C1, C2, C3, C4. Each of those represents one of those columns. Or partition it by rows. And then you have a column matrix of rows. R1, R2, and R3. Okay, they do all that. And we never really do much with that again. So that's why I didn't want to write all that down. I did want to go through this because, number one, it showed Alea what we were doing with changing a system of equations into a augmented matrix, the coefficient matrix and the constant augmented together, and then how we do row reduction, because she wasn't here when we did that, and then what happens if you have a variable without a leading one. You set that variable equal to a parameter, and then you they call this back substitution with Gaussian elimination. And you know this stands for x of 2. This is a constant, and this will be 2 times that parameter t. So x2 equal 2 times 2t minus 1, and x1 is equal to x1 plus 2x2 plus 3t is equal to 0. And just plugging in, back substituting until you get all of them in terms of t. So that finishes 2.1. Homework exercises in 2.1 would include, and by the way, Ricky, I know you said you had a PDF book, didn't you? Okay.
Yes.
Okay. I don't think Aaliyah has a book yet, so I don't know. I know you sent one to Jemanuel. I can't say his name today. If that will work for you, if it's easy to do, send one to Aaliyah until she gets one, unless Aaliyah, you think you're going to get one right away. Okay. But anyway, once you get the book, and it's exercise set 2.1. Now, 2.1, as all the exercise set, you'll notice there is a QR code. Well, first the writing. It says see calcchat.com for worked out solutions to the odd number exercises. And actually that QR code you see up there at the end of that line there, if you just do that with your cell phone or an iPad or something, you'll go straight to calcchat.com. So the answers for the odd numbers are in the back of the book. The calcchat.com has worked out solutions for the odd number exercises. So I assign to you the odd number exercises. So what I suggest that you do is try to work as many of these as you feel like you need to. You don't have to work them all. It's up to you. But work as many as you feel like you need to, so you feel like, hey, I've got mastery over this. I understand it. If you can get the answer in the back of the book, move on. If you can't get the answer in the back of the book, see if you can figure out why you missed it. If you can't do that, then go to calcchat.com, and they'll work out the solution for you. Now, I haven't gone there, so I don't know how good their explanation is, but if you find it deficient and you can't still see why or how they did that, then bring it to class and we'll work it through in class. And that way, everybody will get a chance to see how it's done. So, homework exercises, do either 1 or 3 or both. They're both the answers in the back and at calcchat.com. Do any of the odds 5 through 9. They're all at calcchat and in the back of the book. Do either 11 or 13. They're both at calcchat. Do any of the odds 15 to 27. You decide how many of those you want to do until you feel confident you have mastery of it. And that, by the way, is multiplying matrices, and you'll need to go back and listen to the YouTube videos to see how that works. Okay? Do either any of the odds 29 to 35. They're all at calcchat. Do 37. It's at calcchat. Do any of the odds 39 to 47. They're all at calcchat. Do any of the odds 49, either 49 or 51. They're both at calcchat. Do 53. It's at calcchat. Do 55. It's at calcchat. Now they come up with a new definition here, and this sort of aggravates me about how he does the book. I like this author on many things, but periodically he puts new definitions and new meanings in the problem set, not in the regular chapter, which I don't know if it's important. Why not put it there? But here he tells you what a diagonal matrix is. So once he told you that, then you can do number 57. Okay? And then 59 is finding the product of two diagonal matrices. So you should be able to do that one. They're all at calcchat. There's a proof of number 61. Now you can choose to do these or not. That's up to you. If you're a math major, I would say probably get used to doing proofs. If you're an engineering major, you probably try to avoid proofs at every chance you get. And I don't know. I'm just kidding. Okay? Then here's another definition. Before you get to 63, he gives you another definition. What is the trace of a matrix? Okay, you will be using this a little bit, but not that much. So he gives it to you in the problems rather than in the chapter. So review that and then do either 63 or 65. 67 is another proof. You decide whether you want to do that. And it uses traces, by the way. You decide whether you want to do that. It's a calc chat. Then you can do any of the odds 69 through 73. Okay, 73 sort of an exploration problem. So 69 or 71, you can explore doing 73 if you'd like. 75 is another proof, so if you want to do that, you can. That's up to you. It should be at calc chat if you want to see how the proof goes. 77 you should be able to do. It's a calc chat. And then some application problems. I'm sorry. I don't know why this is happening today. Okay. Either 79 or 81 are both application problems. 83, you can do it. They give you something they call block multiplication. They sort of define that, so another sort of new thing there. So you can do 83 if you'd like. 85 is a true-false problem. Its answer should be at calc chat, so you should be able to think through that. 87 should be at calc chat, and you can choose to do that or not. Usually the bigger numbers are a little bit harder, so that's up to you. Let's move on to 2.2, which is properties of matrix operations. Now, how does this differ from 2.1? 2.1 was operations with matrices, and 2.2 are properties of those operations with matrices. Okay? So, let's get started. First subtopic here is the algebra of matrices. Now, you'll get this. We're always going to be comparing how matrix operations compare with real number operations. Remember, you can add real numbers together. You can add matrices together, as long as the matrices are the same size. Okay? You can multiply a real number by a constant. That's called scalar multiplication. You can multiply a matrix by a constant, but there's rules for how to do that. Okay? You can multiply two matrices together. Okay, let me go back. You can subtract two matrices, one from another, but you do that the same way you do with real numbers, by adding the first to the opposite of the second. That's how you do subtraction of signed numbers, right? If you do a -3 plus a -7, okay, that would be a -10. You just add the things. But if you do a -3 minus 7, you add the -3 to the opposite of 7, and you still get a -10, okay? So that's how you add. Well, that's how you add matrices too. Or subtract matrices. If you have one matrix, subtracting another matrix, take this matrix and add the negatives of all those elements to the matrix. Again, they have to be the same sizes. Okay? Multiplication. Ooh, the last time we looked at how to do multiplication. Multiplication of matrices is not the same as adding matrices. Adding matrices, they have to be the same sizes. Multiplication of matrices, the number of columns of the first matrix has the equal number of rows of the second matrix. And then the other doesn't matter. Okay, the number of rows of the first one doesn't matter, and the number of columns of the second doesn't matter. The number of columns of the first has the equal number of rows of the second. Okay, and then when you multiply, you get a matrix that's the size of the first size digit here by the second size digit there. Go back and review the YouTube videos. You'll see what we're talking about. So guess what? It's not at all surprising that matrix multiplication is not commutative. Multiply any two numbers together, 3 by 7, you get 21. Multiply 7 by 3, you still get 21. So matrix multiplication is commutative. I'm sorry, scalar multiplication is commutative. Matrix multiplication, no. There's only very special cases in which it is. So that's what we're talking about here in the algebra of matrices. Which of your rules for real numbers also works for matrices? And here they are. I guess I should put them out there for Aaliyah. So I'm going to clear the screen if I can find my cursor. Okay. So here are the given in this theorem 2.1, which describes basically most of the things you need to know about the algebra of matrices. Okay. So here we have, as normal, matrices are written by capital letters. So A, B, and C are all matrices. Not only are they all matrices, they're all M by N. Now that's not an X, that's a by, like a time sign, but it's really not times. M by N matrices. Again, this is how you define the size of a matrix. M by N, where M is how many rows do you have, N is how many columns do you have. So if this was a 2 by 3 matrix, there'd be 2 rows, 3 columns. Okay? And all 3 of these matrices are the same size, M by N. Okay? Now, also we're given that C and D are scalars. This is little c and little d are both scalars. Usually, capital letters represent matrices, little letters represent scalars. Now, I kind of think, why would they use a capital C and a little c in the same problem when it's so easy to get them confused? It's just the numbers they like, the letters they like to use. I would have used something else for one of them. So here are the properties. The first of these, one that I've already alluded to, and that is if you add matrix A to matrix B. Now hold your horses right there. Remember, any 2 real numbers you can always add together. No problem there. Can you add any 2 matrices? No. They have to be identically the same size. So again, for you to even say this, you have to have the same size matrices. And they told you they were the same size. So here's the property. This is equal to B plus A. And we call that the commutative property of addition of matrices. Oops, that's supposed to be an A. It's not coming out to be an A. Okay. Hopefully that looks enough like an A to be an A. A plus B is the same as B plus A. Why? How do you add matrices? Corresponding entries. You add each corresponding entry together, and if you reverse the entries, but they're still corresponding, you're just adding real numbers, and it doesn't matter which order you add them. So sure enough, that's the commutative property of addition of matrices. I'm going to abbreviate that by just COMM. Commutative property of addition. Okay? I'll put a plus for addition. I'm really taking it, but commutative property. And here's how I think about this, to keep it right in my head. I used to use this illustration when we taught on campus. I'd say, I drove from home to campus today, okay? And when I leave, I'll drive from campus to home. And as long as I take the same route, it's the same distance. So whether I'm going from A to B or B to A, I'm commuting, and as long as I go the same route, it's the same distance. So here, whether I do A plus B or B plus A, that gives you the same thing. That's for addition and for addition only. Won't work for subtraction, and we'll see later, or we've already seen that it won't work for multiplication either. Now here's the second of these properties. If you take the matrix A and add it to the sum of B plus C for some reason my pen's not writing well, and I certainly don't write well. That is identically the same as the sum of A plus B added to C. Now this is called the associative property. I'm going to use more than the first three letters for obvious reasons. I'll just stop there. The associative property of addition of matrices. And again, it's just like the same reasoning before. Remember, all three matrices have to be the same size, but they gave us that. They were the same size. They are the same size. As long as they are, it doesn't matter which order you add them. Okay? Because if you add B plus C first, then you're doing B1 plus C1, B11 plus C11, B12 plus C2. You're adding all those corresponding things together, and then you're going, when you get all those done, you get them here, and then you add A1 to it. You have A11 plus B11 plus C11, A12 plus B12. You know, they're all the same. If you did them this way, you have A11 plus B11, A12 plus B12, blah, blah, blah. And then you add C to it, you have A11 plus B11 plus C11. You get the same answer, okay? So that's the associative property of addition of matrices, okay? Now, this is as close as we can come to have an associative property of multiplication. And it's not really very close, okay? If you multiply the scalar c, this is the little c, that's why I really regret they did that. Multiply little c times little d, and then multiply that by matrix A, okay? That's the same as, identically the same as multiplying c by the product of, I can't write, d times A. Now, for Aaliyah's purposes, she wasn't here, how you multiply a constant by a matrix. A constant is a single number. A matrix is a whole bunch of numbers in a fixed rectangular array, okay? If you're multiplying a constant by a matrix, you multiply that constant by every element in that matrix. So if that was a 2 by 3 matrix, you multiply the C by the first entry, C by the second entry, C by the third entry. You multiply them by all 6, okay? So this is saying if you multiply your two constants together first, C times D, gives you a new constant, multiply that by A, and you got CD times A1, 1, CD times A1, 2, CD times A1, 3. By every element, you got CD times it. When you do it this way, you first multiply D times A. So you have D times A1, 1, D times A1, 2, D times A1, 3, all the way down. And then you go back and multiply C by each of those, and you get CD by A1, 1. It's the same thing you got before. So they call this the associative property of multiplication. Now, I don't like that particularly because it's the associative property, and I'm not going to write this down, associative property, and I'm going to put the time sign for multiplication, but it's really not quite true. It's the associative property of two scalars with one vector, with one matrix. That's the only way it works. If you had one scalar and two matrices, no, it's not going to work. If you had 3 matrices, no, it's not going to work. In fact, you probably can't even multiply them, okay? It only works when you have 2 scalars and 1 matrix. So they call it the associative property of multiplication, but it only works if it's 2 scalars and 1 matrix. Okay. Now this fourth one is pretty straightforward. No argument here at all. It basically comes from your scalar multiplication. That's all it is. You multiply the scalar 1 times matrix A, guess what? You're multiplying 1 by every element in A. You still have not changed a single element because you multiply by 1, you get the matrix A. So that's the multiplicative identity element. The multiplicative, I'm just going to abbreviate that, multiplicative identity. Okay, multiplicative identity element is the number 1, just like it is for real numbers. Give me a real number, pi fourths. Multiply it by 1, and what you have? Pi fourths. Okay, you don't change it at all. All right, that's a pretty simple one. Number 5. Okay, number 5 is this one. It's a sort of a distributive property. If you have the scalar c, that's the little c, multiplied by the sum of the two matrices, A plus B, and you can add them because they're the same size, remember? So you can do this, C times A plus B. Okay, what's another way of doing that? You can distribute the C across and do each one. So that's the same as C, that's the little scalar c, times the matrix A plus C times the little c scalar c times the matrix B. Okay, and that is a distributive property. I'm going to abbreviate that, distributive property. Now, normally in real numbers we relate a multiplication over addition, which is exactly what we're doing. So, to be more precise about it, I call it the distributive property of scalar multiplication over matrix addition. Because you see, you're multiplying a scalar by the sum of two matrices. So if I were doing this, it would be this distributive property of scalar multiplication. I'm abbreviating like crazy here. Scalar multiplication over, I'm going to put over matrix addition. Now that doesn't make any sense to anybody unless you heard me say it with it. And fortunately, the class is being recorded and it's in sync, so you should be able to follow what it's doing. Now here's another way you can think of distributive property. This to me is a little bit of a stretch, but it's certainly true. What if you have the sum of two scalars? Scalar c plus scalar d that they gave us at the beginning, and you're going to multiply that by matrix A. Well, the way you could do that is distribute A over both of those. That would be C, that's little c, times matrix A plus little d, scalar d, times matrix A. All right. That's another distributive of its scalar multiplication over scalar addition. Okay, so it's the distributive property of scalar multiplication over scalar addition. Scalar multiplication of a scalar times a vector, but over the addition of the two scalars. Now, those are your 6 properties. Most of the ones you'll need. Some of them you're not going to use that much, but you could do it. They show the proof of one of those. And if you're a math major, probably is worth your time to go over those proofs. But I'm guessing, am I right? Are most of you engineering matrons? Yay or nay?
Yeah.
Yes? Yes?
Computer science.
Oh, computer science. Okay, yeah, that'll be fine. And Ricky? Don't know what Ricky is, but I don't think she's a math major. Okay? So.
What was that?
I'm sorry? I was asking what your majors were. Are you math major or?
Civil engineering.
Civil engineering. Okay, I thought you were an engineering major. Okay, so I'm not sure you'll need the proofs of this. That's why generally I kind of skip the proofs. We don't have time, and they just, I don't know if they. Say again? Okay. All right, so let's do example 1. And I think I'm going to need to clear the screen. Does anyone need these a little longer? No? Okay. All right. So what if we're adding more than 2 matrices? Okay. Here are the ones we're wanting to add. Now these happen to be column matrices, which you could call column vectors. Okay. The first one is 1, 2. And add to that, if I can get my pen to move, the vector, column matrix, -1, -1. Pretty ugly writing, I admit. Add to that the matrix 0, 1. And add to that the matrix 2, -3. Okay, and let's see what we get. Can you add those 4 matrices together? Yay or nay?
Yay.
Yay, yay, we can. Okay, and why can you do it?
They're all the same size.
They all the same size. That is exactly right. And what size will your sum be?
The same size.
The same size. And what side is that?
2 by 1.
2 by 1, exactly. 2 rows, 1 column. So you're going to wind up with a column vector. I'm just going to put blanks there for us to fill them in. And how do you add these? As long as you're doing the same elements, you can do them in any order you want to. Well, that first one, because they're both commutative and associative, 1 plus a -1 is going to be 0 plus 0. I can do that, and that leaves you with what is your answer?
2.
2, perfect. And in the second element, let's see, I think I'll add these 2 first. 1 plus -1 is?
0.
0. Plus 2 would be 2. Minus 3 would be?
-1.
-1. Perfect. You can do that. And that's exactly what they got in the book. Good for them. Now, they didn't put the lines under it. You don't need to. I just do it to help. Let me see. Now, I wanted to say this when we were doing it, when we did those operations. They gave a multiplicative inverse, but they didn't do an additive inverse. So that's what they're going to get to now. I'm sorry. Oh, boy. My stomach is saying, feed me, feed me. We've still got 45 minutes to go. Not quite, but close to it. Okay. One important property of addition of real numbers is that the number 0 is your additive identity element. Okay? That is, any element, any number you have, 4/3 pi, plus 0, you still have 4/3 pi, the additive identity element. Okay? Now, in matrices, because you can't add just any old thing to a matrix, it has to be a matrix of exactly the same size. So therefore, you can't say there's one single additive identity element. but you can give it a generic name and call it the zero matrix and make that the additive identity element. Now the thing is, the zero matrix is just any old matrix that has zeros for every element. So you almost have to specify the size. And here's how they do this. The zero matrix, and they use, it looks like the letter O, this time is the number O. And the one they give in the example is a 2-3, I think, or do they give it a 3-2? Yeah, 2-3. 2-3. If you're adding a bunch of 2x3 matrices together, anything, and you want to, the additive identity element, here would be the matrix you would have to use. You'd have to use one of the same size, a 2x3. Can anyone want to hazard a guess of what those elements will be? 0, 0. If the pen was right, 0, 0, 0, 0. A whole lot of nothing, right? That's your zero identity element for adding 2x3 matrices. It's the 0 2x3 matrix. Every element is 0, and when you add the elements of the other to that, nothing changes for any of those elements, so you wind up with the same matrix A you started with. So matrix A plus the 0 matrix of the same size is always going to be matrix A, the additive identity element. All right. Now, when the size of that matrix is understood, you don't need to write the 0 or the O23. What you can do is this. Okay? Let me make sure I'm doing this right. Yeah. You can name that matrix this. Only I'm going to put an arrow over it because I can't write a bold. In the book, it's going to be bold. And since bold usually to me means vectors, this isn't a vector. This is going to be the 0 matrix. It's going to be the most matrices we name with capital letters. This one we name with the number 0. Not O, 0. And then make it bold. In the book, it's going to be bold. Since I can't write bold, I put an arrow over it. That indicates the 0 matrix. When you understand that it's what size it is, because it could vary from problem to problem. So, the following set of properties then are the properties of 0 matrices. And these, they say, are all relatively easy to prove, and they go through a little bit. So here are the three properties of a 0 matrix. And let's start with the given. The given is you have a matrix A. And I think this matrix A is not the 0 matrix. So A is an M by N. What does that mean? That's the size, and what does that mean? Say again. M rows by N columns. Perfect, perfect, perfect. And again, C is a scalar. I'm just going to put SC for scalar. Okay. Then here are your three properties of 0 matrices. The first of these. These are always true. If you add matrix A by the right size of the 0 matrix, add it to the right size of the 0 matrix. In this case, this 0 matrix, I'm not going to put the generic form, I'm going to put M N. Now, it's all right to put M by N, but a lot of times when they're writing in subscripts, they just put MN. Okay? Add the proper size, M by N matrix, 0 matrix, to an M by N matrix, you're always going to wind up with matrix A, because every element's being added to 0, and when you add any element to 0, it stays whatever element it was. Okay? First, pretty direct. Second of these. And by the way, when I say little things like that, I'm really giving you the proof in a shorthand. Okay. Let's say we start with matrix A. And we add to matrix A the exact opposite of A, negative A. Guess what you're going to get as an answer? Every element is added by the opposite of that element. Guess what they all become? They all become zeros, so therefore you're going to produce the 0 m by n matrix. Okay? And that was the same in real numbers. Give me a real number, any real number in the world. Give me one. Anybody?
3.
3. What's the opposite of 3?
-3.
Negative 3. What happens when you add 3 to negative 3?
Get 0.
You get 0. Same thing here. If you have a matrix A, add the opposite of matrix A. That means you've negated every term in that matrix. Add those two together, you're going to get the 0 matrix of the right size. Okay? And here's the third of those properties of the 0 matrix. Pretty ugly 3. Okay. If it's a conditional situation here. If you know that you have a product of a scalar, that little c, times this matrix A, and if you know when you do that, you're going to wind up with the 0 matrix of that size Mn, what do you think you can conclude from that? If that's the given, what is the conclusion you can make? Either one of two things. Either C, that scalar, is identically and only equal to the number 0. That's the number 0. Or that A itself had to have been the 0 matrix of size Mn. One of those two had to be true. You can't get the product of 0 without one of the two factors being 0. Same thing that we use when we're solving equations. If if A, B is equal to 0, that tells me either A is equal to 0 or B is equal to 0. No way around it. One of them's got to be 0. Okay? Well, if C, scalar C times matrix A is the 0 matrix, Mn matrix 0, then either C had to be 0 and A could have been any M by N matrix, or C, if it wasn't 0, that meant that A matrix had to have been the 0 Mn matrix to begin with. So this is 0 product principle, similar to what we had before. Now, much of the algebra of real numbers and the algebra of matrices have many similarities. And here's a couple. But don't get carried away. Okay? I think I'll go to a clean page. Can you, all right, to clear this?
Yes, sir.
Okay, good deal. All right. Here's an example. If you have an equation, scalar equation, x plus a is equal to b. Okay, scalar equation, x plus a is equal to b. Okay, now, how can you go about solving that? X is the variable, a and b are constants. Subtract the a from both sides. And you can conclude that that variable x, this is high-level algebra, isn't it, is equal to, because see, these two add to 0, b minus a, right? Simple one-step problem, okay? No questions asked, right? Well, what if we had a bunch of matrices? Now, of course, they have to be the same size. So you have an unknown matrix X with variables in it, and you're adding that to the same size matrix A. Has to be the same size, or that doesn't make any sense. And you know that this is going to produce the same size matrix. It has to, or it wouldn't make sense. B, then you can similarly say that X, matrix X, could be found by subtracting A from B. Okay? Same thing works for matrices. Okay? So, example 2 here is going to do the same type thing. Let me just keep up with time here. Okay, we've got 30 minutes left approximately, right? My stomach's telling me it should be sooner, but it's not. Okay? So, if you know this equation's true, that 3 times some unknown matrix X plus some known matrix A of the same size, it has to be to make sense, and this is equal to some other known matrix B of the same size, it has to be, otherwise this makes no sense at all. It says solve for that X given these two matrices you know. Here's matrix A, pretty simple one. 1, negative 2, 0, 3. 1, negative 2, 0, 3. There's matrix A. 2 by 2 matrix. Guess what size B has to be? Also has to be 2 by 2. Sorry, here we go again. I don't know what's going on. B has to be 2 by 2. Its entries happen to be negative 3, 4, 2, 1. Okay? Now, how would you solve this matrix equation? Just like you would a scalar equation. As long as they're legal steps. You subtract matrix A from both sides. Okay? And that leaves you 3 times the unknown matrix X is equal to, because the A's added to 0 here, okay, B minus A. Oh, that's an ugly A. Just imagine that's an A. And then what we'll do is divide both sides by the scalar 3, which could be interpreted as multiplying by 1/3. In fact, that probably would work a little bit better. But let's just do it. Okay? Let's first subtract. I'm going to put the 1/3, multiply by 1/3. So I'm going to put that on the outside. And now let's do our difference matrix here. B minus A. So we start with B and do it component by component by component by component. Okay? Negative 3 minus 1 would be?
Negative 2.
Negative 3 minus 1. All right. Send them back to algebra class. Okay. Okay, next. 4 minus a minus 2 would be? Minus a minus makes a plus. 4 plus 2? 6. Very good. Got them gun shy now. Okay. Next, 2 minus 0 would be 2. And 1 minus 3 would be
-2.
-2. Okay. So we got that part done. Now we take 1/3 of every element in there. Okay. First element would be a -4/3. Second element would be a 2. In the second row, first element would be a 2/3. And the second element would be a -2/3. I don't know why my pen is skipping now. It's just started doing that today. It didn't used to skip like that. Okay. All right. Let's see how the book did. They got -4/3 too. 2/3, -2/3. Good for them. They got it right. I'm so proud of them. All right. All right. We talked about properties of arithmetic operations. That was our first theorem. Okay. And we did some commutative, associative, few distributive, few like that. Then we looked at properties of your zero matrix. All right, what we haven't touched, though, is how about multiplication? Properties of matrix multiplication. This is the subtopic at the top of page 54. Okay? Now, clear the slide. Okay? Anyone need it longer? Okay. Here we have 3 matrices. A, B, and C. These are all capital letters A, B, and C. Now, these are matrices. Okay? Do you think, okay, since we're doing matrix multiplication, you're going to say of the same size? No, you don't. You say that with sizes that the matrix products are defined. Okay? So how I'm going to express that is of appropriate sizes. Okay? The sizes that will make your matrix multiplication defined. So the first thing we're going to do on these properties is identify what size you're dealing with. And once we've got those, then we'll be able to go from there. Okay? Now, and what we have is C is little c is C is a scalar. And again, why did they have to use the same letter? This is a scalar. So A, B, and C are capital A, B, and C are matrices. Little c is a scalar. So here are your properties. First, if you do, oops, I messed it up. Okay, get it back. All right. If you do matrix A times the product of B times C, okay. Now here's what they claim. That's going to be the same as the product of AB times C. And that's going to be associative property of multiplication. Associative property of multiplication. I'm not going to write out all those words, but do it. Now, here's what I'm saying you have to make sure is true. Since we're starting with matrix B and C, that's the first operation we're going to do now, and then multiply by A. So you give me a generic size for B. Make it letters. Don't make it numbers. What size do we usually name it? MN? Is that okay?
Yes, sir.
That keeps it generic. Now, if that's the size of B, what size does C have to be?
N by M.
N, not necessarily by M. It could be
Yeah.
any other letter in the world. So let's use P, okay? The reason I don't want to use an O, it looks like a 0. Okay? Now, this matrix multiplication is defined. You have to have the same number of columns of the first by the number of rows of the second. You do. And what size will this product matrix be once you multiply it?
M by P.
M by P. Absolutely. Now, what size does that make A have to be? The first letter can be any letter that we haven't used already. What letter you want to use?
L.
No, we've used M. How about Q?
L.
Q, okay?
Yeah, yes,
But
sir.
what's the second letter got to be?
M.
It's got to be an M. You're absolutely right. So A is a Q by M, B is an M by N, C is an N by P. Now some of these could be the same or different, doesn't matter, but the ones that there have to be. All right? And what's the product of these two going to be? QM by MP,
QP.
QP. Okay, QP doll. Okay, never mind. QP. That's a Q. It doesn't look like it. All right. Now, let's see if that will work, at least by size. We don't know if the numbers work out, but at least by size it better work. If the size doesn't work, the whole property doesn't work. Okay, A we said was a QM, right? We said that at the beginning. That's a QM, Q by M. And B we said was an M by N. Okay, and C we said was a N by P. Okay, that's what we said before, so it still has to be true. Can you multiply A by B? It's a QM by MN.
Yes, sir.
And what size do you get?
QN.
QN, okay? That sounds like a question to me, okay? Can you multiply a QN by an NP?
Yes, sir.
You can. And what answer will you get?
QP.
I get you like those QP dolls, don't you? Okay. So there's a QP. So at least by sizes, if the sizes are appropriate, that works. We haven't guaranteed the numbers work, but at least the sizes work. So we'll say, yes, okay, multiplication, as long as they're the right sizes, is an associative property. Multiplication of three appropriately sized matrices. Okay? Number 2. Looks like I might run out of room. I'll figure out something. Number 2. Now here's the claim. That A, matrix A, times. Now these don't have to be the same sizes as the others. These are appropriate sizes, so we'll have to figure this out. In fact, you'll see right now that they almost can't be the same as before. B plus C okay. Their claim here is that this is AB plus AC. Okay, writing is getting worse and worse. My hands are getting tired. So tense. Okay. Now again, let's start with over here. Since the first thing we're going to do is add B and C together, since that's in the parentheses. Make up a size for B. Want to start with an M by N as before? that okay? What size will C have to be?
N by something.
No. This is an addition here.
Oh yeah, addition has to be M by N.
It has to be an M by N, okay? And when you add an M by N to another M by N, what size do you get?
M by N.
M by N again. You're absolutely right. So you see, they can't be the same size as up here or they'd never work, okay? Unless they were all the same, okay? Now, and square at that, okay? What size would A have to be?
Something by M.
Okay, we'll make it something of P. Is that okay? Something by M. You're absolutely right. And the product would be then a product of those two would be a what size?
P by N.
P by N. Absolutely. All right. So here we have A being a P by M. Sounds like it's in the afternoon, doesn't it? PM. I can't get the pen to write. Where B, we said, was an M by N. I'm really cramped there, am I not? Okay. Can you multiply those two together? A PM by MN?
Yes, sir.
Yes. And what size do you get?
P by N.
B by N. Okay. And here, this A, remember, was an PM. Like a Tylenol PM. Okay. And C, we said, was an MN. And can you multiply those two together?
Yes, sir.
Yes. And what size do you get?
P by N.
P by N. Now then the next question, oops, that's an N. Stop too soon. Can you add a P by N to a P by N?
Yes, sir.
Yes, you can. And what answer you get?
P by N.
P by N. You're absolutely right. So at least by the sizes, the second rule, and we call this the distributive property of matrix multiplication over matrix addition. Okay, so I'll just leave it distributive property. That's how we usually refer to it. All right. Number 3. Let's try to write that here. All right. Goodness, I'm getting so hungry. All right. Number 3. We're going to start with matrix A and add to it matrix B and multiply that addition, that sum, by matrix C. And the claim here is that should be the same as A times C plus B times C. All right, let's see if that makes sense. So the first thing we're going to do is add these two together, make up a size for A. Anybody? You want it to be our standard? M by N? If that's the case, what size would B have to be?
M by N.
It has to be an M by N also. And what's the sum of two M by N's going to be?
M by N.
And M by N. I'm getting tired of writing that, okay? Now, what size would C have to be?
N by something.
N by something, so let's just call this something a P. Why not? NP. Can you multiply those?
Yes,
MN,
sir.
yes, and what size would the answer be?
M by P.
M by P. Perfect. Okay. Now let's go over here. We said that A was an M by N. That's an ugly M by N. The C we said was an N by P. B we said also was an M by N. And C again was an N by P. Oh boy, are my hands crampy. Okay, if you multiply these two together, an Mn by Np, what size do you get?
M by P.
M by P. Multiply this, B times C, M by N by P, you get an
M by P.
M by P. And can you add two M by P's together?
Yes, sir.
And that gives you military police, right? Okay, MP. Good deal. And an MP, well, at least by size, they seem to work. And we'll say, yes, they do. All right, now the fourth one. Hopefully this won't be quite as bad, but who knows? My hands are getting really tired. What if we have that little c scalar, this is a scalar, little c, multiplied by the product of two matrices, A times B. Now their contention here is that this is going to be the same as CA, C times A, multiplied together times B, and that also, that's supposed to be a B there, that also that's equal to the same as A times the product of C, little c times B. That, I think, is what they're claiming. And, oh my goodness. So give me a generic size for A.
M by N.
M by N, I thought you might say that. And then give me what has to be a potential size for B.
N by M.
It could be by M, but let's make it more general and make it N by P. Okay? It could be M. You're absolutely right. And P could equal M. No problem. But N has to equal N. Okay? And what's the size of this one going to be? Another military police, right? MP. And guess what? Multiplying a scalar is not going to change your size at all. So again, if this A was an M by N, which is what you chose to begin with, an M by N, and you multiply it by a scalar, you still get an M by N. But then you multiply it by B, which you said was going to be an N by P, or at least you and I together said that. And can you multiply M by N by N by P? Sure. And you get an MP again. That's what my stomach is, MP. No, MT. Never mind. Okay. What was your A? An MN. B was a NP. Right? Yeah. Multiply C by an MP. C, hey, guess what? C is a scalar. Doesn't change the size of your product. That's going to be an NP. And can you multiply an MN by an NP? Sure you can. That gives you an MP. Now that doesn't make the numbers come out, but if the size didn't come out, you can't do it. So at least it tells you the sizes are right, and they're telling you by the statement that these are true. Now they do a proof for the second one there. So I'll let you work through the proof if you're interested, which I'm sure you are, okay? And you can go from there. Okay. Let's do example 3. Okay. Find the matrix product ABC by grouping the factors first as AB times C and then as A times B times C. Okay? So we're first going to do AB if I could write. It's getting worse and worse the hungrier I get. I'm soon going to be eating these letters. Times C, and then we'll do A times BC. And we'll see if the numbers work. We sure hope the sizes will work, so let's verify that to begin with. All right, so here's our A. It's a 2 by 2. That's a 1, -2. And a 2, -1. Here's our B. It happens to be a 2 by 3. 1, 0. That's a terrible 0. My pen's not writing. 2, 3, -2, 1. I didn't leave enough room, so I'm going to write C over here. And C's a 2 by 3. No, I'm sorry, I said it wrong. 3 by 2. -1, 0. 3 by 2. Okay. 3, 1. And a 2, 4. Oh my goodness gracious, I'm so hungry. All right, let's first multiply A by B. Okay, Aaliyah, this will be a new exercise for you. 1, -2, 2, -1. Okay, multiplied by B. Whoa, that's awful. Okay, and that I think is a 102 multiplied by 3, -2, 1. Okay. Now first, before we do anything else, can we multiply these together? What's the size of A?
2 by 2.
2 by 2. What's the size of B?
2 by 3.
2 by 3. Can you multiply those together?
Yes, sir.
Yes, you can. The reason you can, the inner numbers are the same. The number of columns of the first is equal to the number of rows of the second. So you wipe those out. That gives you a product matrix being what size?
2 by 3.
2 by 3. So therefore, I'm going to write the product matrix. I can't write the numbers in, but I can write how big it is. It's going to be 2 rows and 3 columns. So these blanks are going to be where I'm going to put the entries. 2 rows, 3 columns. Now here's our review of matrix multiplication. Okay? You find the name of this entry here. What's the name of this entry?
A1.
Okay, A11. First row, first column. We use that fact, first row, first column, to do the first row of this one times the first column of this one. And you multiply and add as you go. So 1 times 1 is
1.
1, plus a -2 times 3 is
-6.
-6. So 1 plus -6 is
-5.
-5. So there's your first entry. Okay, what's the name of this entry here?
A sub 1, 2.
1, 2. First row, second column. So we do the first row of this again. Now, I did not draw that. It's just throwing in marks wherever it wants to. Okay, I'm going to see if I can erase the mark wherever I want to. Okay. Sorry about that. All right, we've got, oh my goodness, yuck. We're out of time, aren't we?
Yes, sir.
All right, sorry about that. Went to all that effort not to be able to do it. So we're going to do example 3 next time. That's where we'll lead off next time. And
Mr. Fowler?
yes.
Where's the test 1?
Where's what?
Test 1.
Okay. You go to messages. You know
Okay.
where to do that on Blackboard? It's a thing that looks like a little envelope.
Okay.
Okay. And you look there, and probably the only thing you got from me there is test 1. There may be other students sending messages, but the only thing you get from me is test 1. All right. Let's see on this set 2.2. Sorry, if we did enough to do any exercises on page 59. I think you can do any of the odds 1 through 5. If there are answers in the back, but they're also at Calc Chat. I think you can do any of the odds 7 through 11. They should be all at Calc Chat. I think you can do 13. It should be at Calc Chat.
We can't hear you, Dr. Fowler.
All right, sorry about that. On page 59, exercise set 2.2, do any of the odds 1 through 5. They should be at Calc Chat. Do any of the odds 7 through 11. They should be at Calc Chat. Do number 13. It should be at Calc Chat. And I think we'll stop there because after that we're getting into multiplication of matrices. We haven't done those examples yet, so we'll hang off. So stop at 13 here. All right. Now, just a little reminder, and this is mostly for Aaliyah, but anyone else who hasn't done it. I don't remember if I even told this class, but I should have. The assignment for the first day of class was to write or sign your name to the last page of the syllabus to let me know that you have read it, you understood it, you asked any questions you had, and that just lets me know you've done that. So that was the assignment for day 1, okay? And then the other assignments have been any of the odds from any of the problem sets. You don't have to do them all. 1 is sufficient, okay? So now that you have a test out, though, don't worry about sending me any homework problems. Focus on the test, okay? But as soon as you get the test done, then start working at least 1 problem from each exercise set to send to me, so I'll know you're still working on things. Okay? So that yes.
When I looked in the messages, I didn't see the test.
Okay. So hang on right now and let me see. I've got to go to you're going to lose the screen for a minute, but I'll get it back to you as soon as I can. I'm going to Blackboard. Okay, I have to do it sort of a strange way, but you can't see what I'm doing, but that's sort of good. Okay, it's kind of a mess to get to. Okay, I know the screen has paused. Okay, trying to get to Blackboard. As soon as I get to Blackboard, gotta log in first. Okay, this is a long, stupid process. Okay, and when I finally get to Blackboard, I'm going to go to Courses. Okay, and that's where I'm going to bring the screen back up. And see if this is the screen. Yes, do you see that? Do you see my courses?
Yes, sir.
Okay, so let's go down here and scroll down till we find this course. 237 Summer. That's us. Okay. Now you go up here to the envelope, right? It says messages. Click on that. And there I see it on mine. Do you not see it in yours? MTH237 Test 1. It's a PDF.
When I clicked on it, it didn't show up in mine.
Okay, let me try that. Okay, you don't click on this. What you have to do is go to the three dots. Click on the three dots. Click once on the three dots. It says download the original file. Click on that. And then down here in the lower left corner, you'll see it. Click on that. And there's the test. And you have to do it laying down. Yeah. It's a 2-page test. There's the first page. And there's the second page. Okay? And hopefully you can print those off. And obviously someone was not in the right mind when they were doing this. And everything's a little catty-cornered. But when I'm holding an iPad over it trying to get it, it takes a picture whenever it wants to, not when I want to. So sorry about that, but hopefully you can follow everything. Do you see how to get it now?
When I click on messages, it just tells me like this is where you view your messages for the course, but it doesn't have anything in it.
Okay, so you didn't see the same thing I just showed
No.
you. Okay. Now, I don't know why that's the case. You don't see this screen right here.
No.
Okay, do the rest of you see the test in yours?
I see it, but I assume because they joined late that it only sends to the students that you had currently registered when you posted it.
Is that right? I love this Blackboard Ultra. It's so reasonable. Okay. So I guess what I have to do is post this test again. Let me see if I can do this. Can all the rest of you see the test? All three of you. James, Jermanuel, and Ricky. Can you all see the test?
I can see the test.
You can, all three of you. Okay,
Yes, sir,
so
me
what
too.
I'm going to do is I'm going to send a message to, well, I can't do it with these things in the way. James, you're in the way again. Okay. Okay, I'm going to add a message. Okay. And that new message, oh, I've got to get my file up. Sorry, this is taking longer than I thought it would. Okay. So what I'm going to do is, I can't see. James, you're still in the way. Could you get out of the way, please? Okay. I'm going to send it to all of you. Okay, all course members. And I'm going to attach the file from a local file. And that takes me to oh no. Let me back out of this again. Okay. Let's do a local file. There's something wrong here. I plug in my, oh, there it did. First time it didn't connect. Okay, I'm going to local file, and oh, it came up. Okay, I'm going to my math things here. I think is where I'll put it. And this is 237. And here's test 1 in PDF. Okay. And then I'll send the same message. Oh, I blew that. Sorry about that. I forgot. You have to. I really do love this. Okay, let me do it again. The PDF file. I have to save it first. Now I can do the message. And it says attached is the chapter 1 test. And we'll send it. And all 4 of you should get that. I don't know how long it takes to show up. But it should be there. And what I'm going to do, I'm going to trash the first one. Now you might think, why would I want to do that? No. Here's the first one. You might think, why would I want to trash the first one? Because if Blackboard decides to put a date on it, due date, which I don't think it's done yet, but if it would, it's going to have to do it to the new one. So I'm going to...
I got the document.
You got it. Okay, good.
Yes.
And it looks just as bad as it did before, didn't it? Never mind. Okay. All right. So everybody's got it now. Sorry about that. I didn't know when you went into Blackboard you wouldn't get everything that everybody else had in Blackboard. That's sort of crazy. But I guess because it does go to just the individuals in there, that must be it. All right. Good deal. Any other questions, concerns, issues? Okay. If not...
When is the test due?
Okay. What I usually say, I always give you at least a week. And the reason I say that, it gives you at least one day of class to ask questions if you need it. If you need more time than that, take it. But try to get it into me before we finish Chapter 2. Okay? Because I'm going to be giving you Chapter 2 tests, and I don't want you to have them piled up behind you. So I'd rather you get it in sooner than later, but take the time you need to do it well and do it right. I know that you've got to catch up on everything, so take your time, but work at it as you can. Okay?
Okay, thank you.
All right. Now, once it gets in the grade book, Blackboard assigns a due date. Ignore it. Okay? I haven't put it in the grade book yet because no one's turned it in yet. But once the first person turns it in, Blackboard assigns a due date. I love Blackboard. It's just wonderful. Okay, so never mind. Okay, any other questions or issues? Good deal. Glad you asked that. Glad you pointed that out. I wouldn't have known it. So I'm going to stop the share now. Is that okay? And then I'll also end the meeting unless there's any last parting shots. None? Well, bye-bye. We'll see you on Thursday. Okay?